Okay, we start now. So now next talk is by Pavel. We'll talk on functionality of a graph is square root of the number of vertices.
Thank you for introduction. So this is a joint work with Lukáš, Folwarczný, Michal, Opler, Pavel, Pudlák, Robert, Šámal, and Untitled. So it's about a slight new parameter called graph functionality, and it's somehow generalization of a degeneracy, which probably I hope most of you know. So what's degeneracy is a maximum over all induced subgraph of a graph, and you take a vertex of minimum degree in that graph. So in words, it says degeneracy of the graph is least number such that any induced subgraph has a vertex of degree at most this number. And so this is the formula for it. And when you replace the degree of a vertex by functionality of the vertex, you get functionality of the graph, right? So what's a functionality of a vertex? So it's minimal k such that the vertex is a function of some k vertices. So what does it mean? So we say the vertex y is a function of k vertices if there are k vertices, x1 up to xk, let's say it's a set S, and some function from k bits to 1 bit, and the neighborhood of y in this set S determines all neighbors of y. So what does it mean? So we have other vertex z, and we are interested in if z is connected to y or not. We check the neighborhood of z in S. Let's say it's connected to x1 and xk and not connected to the other vertices. We represent this as a vector. 1, there is an edge. 0, there is no edge. For this vector, we applied our function f, and if f is 1, it means there is an edge between y and z. If f is 0 on this vector, there is no edge between y and z. So this is somehow like formal definition. So how this look in combinatorial way? So we can interpret the function f also as a function from all subset of S to 0, 1. Take like the 0, 1 vector on k vertices as characteristic vector of the subset. And the graph looks like this. If we take some subset of S, let's say S1, and we take all vertices that are the neighborhood of these vertices in S is only S1. So they are connected to S1, not connected anywhere else. So this function f is constant on these neighbors of S1, and it means that if fs1 is 1, that all vertices in this potato is connected to y. And if let's take neighbors of S2, and if f is 0 on S2, then no vertex is from another potato is connected to y. So this is how the remaining vertices are somehow grouped into buckets according to neighborhoods to S, and each bucket is completely connected to y, or none of the vertices in the bucket is connected. And why this functionality is connected to degeneracy is because degeneracy is upper bound of the functionality. Why? Because the degree of the vertex is trivial upper bound of the functionality of the vertex. Why? Because we can put all neighbors of y into the set S and then no other vertex is connected to y, so we can take f to be constant 0. So is somehow this notion is clear, or there are some?
So the set S depends on the y. For each y, there is.
So we are looking for one vertex y. And for this vertex, we are looking for set S of at most k vertices. So yes,
And the function also.
Yeah.
The different vertices.
Yeah. So we are maximized. So the functionality of a graph, we maximize it over all induced subgraph. And in any induced subgraph, we are looking for one vertex y for which exists this set S. So it's a little like the structure of the flavor is really as degeneracy. Only like what you count at the end is a different notion.
But the same vertex, when we think of it as a vertex in a certain induced subgraph and in a bigger induced subgraph,
we can take a different sense.
Yeah, we can take that.
And it was this notion was introduced quite recently, somehow implicitly in 2015, and explicit definition published in 2021. And of course, you asked like how this notion appeared. So if a functionality of the graph is at most k, then it can be represented by this.
Just try to understand this. So here's a vertex y, yes, and there is some other vertex z, and I want to know if z is connected to y.
Yes.
So there is these favorite experts F. I ask them, is Z connected to you? Okay. For each of them, you ask whether.
Exactly.
And once I get this information, I'm able to tell whether.
Exactly. And like this set S is universal, so like it is the same for all others.
All others Z.
Yeah.
Once Y is close.
Yeah. Y is statistic and all for all other Z. This information will tell you if it's connected to Y or not. So if a functionality is at most k, so let's say k is constant, then G can be represented by at most n log n bits. It's not very hard to deduce it, and it follows that if we have some class of graph that all graphs has a bounded functionality, that if you look on the graphs in this class that have n vertices, then there are at most 2 to n log n of them, and we says that such a graph class has a factorial speed, and the functionality was introduced to study so-called implicit graph conjecture, which says that any hereditary class of factorial speed has efficient implicit representation. So a hereditary mean is closed under the induced subgraph. And what's efficient implicit representation? It's not very important. It's not important for this talk, but that you had an idea how this notion was introduced. So we have some class F, hereditary class, and we take some graph G, and we want to assign labels of size at most log n bits to all vertices in the graph G, and then there is some decoder, and it takes two labels, and only the decoder does not know the graph G. It knows only the class from where G is, and the decoder gets 2 labels, and it has to decide if there is an edge between these two vertices or not. So somehow you can see that the flavor is somehow similar, that you have some information, and from that you should deduce if there is an edge or not. However, this recently this conjecture was disproved, but somehow the parameter remains. So, first, we are interested in the conjecture. Then we realized it's too hard for us, so we started to study the parameter and like the functionality.
Oh. So what is factorial speed mean?
It's this that if you look on the class and take all the graphs which has n vertices, then you have at most 2 to n log n of them.
That's the definition.
Yeah. Okay, so now what was the known results about the functionality? So it was related to other graph parameters. So it's upper bounded by clique width, and there exists some function that VC dimension is upper bounded by G of functionality of G, and it was also proved that functionality of hypercube of dimension D is at least D over 3 basically, and of course it is at most D because D is a degree of the cube, and it means that the functionality of hypercube is log n because hypercube has 2 to the vertices. And there is a line of other results that some classes of graphs have constant functionality, like line graph has at most 6, permutation graph at most 8, and so on. So this is known results, previous results, and what's our results? So we prove that if you have a graph of so there is a graph on n vertices such that it has functionality at least square root of n. So as far as we know, this was first polynomial lower bound for the functionality. That previous ones was only logarithmic, and also we have basically matching upper bound that every graph on n vertices has a functionality at most square root n log n. And other results is that actually a random graph has a functionality asymptotically log n. So as you will see, so most of the graph has small functionality, logarithmic, and as you will see, the example of the graph with high functionality is very structured. Yes.
The example that gives you omega root n. What's the degree? It's around root n, or
yeah, it's root n. You will see so today I will speak about the first result. I will not speak about the result. Okay, so what's the lower bound? So the graph with high functionality is an incidence graph of finite projective plane of order k. So I don't know who knows what's a finite projective plane here. Okay, some of you. So it's some combinatorial object. You have ground set of points and family of subset of these points called lines. And it's very structured that each line, so if you have a finite projective plane of order k, then each line has k plus 1 points, and each point lies on k plus 1 lines. And there are many more properties, like every 2 lines intersect exactly on at most 1 point, exactly 1 point even, and it's like 2 points define but through 2 points there is only one line which can go through, and then so on and so on. And so we know that if K is prime, that such object exists. And so what's incidence graph? We take it's bipartite graph. One part is for the points, one part is for the line, and there is an edge between points and line if the point lies in the line. And such graph has basically k-squared vertices. And the claim is that each vertex of this incidence graph has functionality at least k+1. So at the end, it will prove that the graph has functionality at least square root of n. So I will somehow sketch the proof on example. So this is a finite projective plane order of 2 called funnel plane. So this circle is also a line. And how we prove it? So we take one vertex in graph G. Because the graph is very symmetric, we don't care if V is a line or a point. So let's say V is this line, and let's suppose the functionality of this vertex V is 2. It means there are 2 vertices that determine the neighborhood of V. So on the left, this is the plane. On the right, it's part of the G. So x1 is this line, x2 is this point. So because x2 does not lie on V, so there is no edge between V and x2. And we would like to find some. So the question is V function of S? And we will show that it's not, because we will find 2 vertices that it's not connected to S at all, but one is connected to V and the other is not. So this will disprove that S is V is function of S. So we can find one vertex U which is on the line V. It means it's connected in the graph. U and V are connected, but U is different from the point in S, and also does not lie on lines in S. So here U is not on line x1, so U and x1 is not connected. And there is another vertex here, W, that does not lie on V, so there is no edge between W and V, and also does not lie on x1 and is different from x2. So it's not connected to S as well, but U is connected to V and W is not connected to V. But if V would be function of S, then both of them has to be connected to V or none of them. And so basically, this is flavor of the proof, and you can prove it for like arbitrary.
What do you tell about that arc?
This arc, like this is one of the line in the projective plane.
And that x1 and x2 you use for like the same.
Yeah, you need to verify. So I just choose that here.
First, that you are taking 2 subset x1 and x2.
No.
Or like x1 and x2 they are single vertices.
No. This x1 x2 is some representation of some example of the set S. We try to verify that V is not function of S, which is consists of x1 x2. In the formal proof, you need to verify somehow or argue that this does not hold for any S of 2 vertices. Here I show you just like one example to illustrate it.
So in the The example of a projective thing, what lower bound do you get for the degeneracy? Lower bound and upper bound. Do you also get something for this family of graphs?
Degeneracy.
Yeah.
Because
we know the functionality is at least this much, you know that the degeneracy is at least this much. But I don't.
Yeah, so the degeneracy is also K, right? Because if this graph is K plus 1 regular, okay, so
you know this.
okay, so few remarks. So as I said, just G is K plus 1 regular, so functionality of G is exactly K plus 1. And somehow each proper induced subgraph of this graph has a degree, has a vertex of degree at most K. So functionality of any proper induced subgraph is at most K. So somehow this graph is somehow minimal in the case is a minimal in a sense that it has a functionality K plus. Okay, so some question for lower bound. So I will move to the upper bound. So we show that in each graph there is a vertex of functionality at most square root n log n. So we distinguish two cases. So first case is there is a pair of vertices such that their symmetric difference is at most d, where d is square root n log n. So what symmetric difference of two vertices is you take two vertices and count the private neighborhoods of u and v. So you look at all neighbors of u and all neighbors of v, and you count the neighbors only, the vertices that only are connected to exactly one. And it's quite clear that the functionality of the vertex is at most symmetric difference of two vertices plus one. Why? Because in the special set F, we can put the private neighbors of u and v, and then the vertex u, and all other neighbors, or all other vertices are connected to v if and only if it is connected to u. So if we have in our special set F, or all private neighbors plus vertex u, this set determines the neighborhood of v. So this is somehow the easy case. The other case is that for all pairs, the symmetric difference is large. And in this case, we show that all vertices has a small functionality. We pick v, and we pick the set S randomly. And we put each vertex into S with the probability d over n. It means that the vertex S is somehow the size of S is basically d, which we want. The question is v function of S? And we show that v is not a function of S with probability smaller than 1. So there is a set S of a right size that v is a function of that set. And why this is true? So suppose v is not a function of S. So again, it means there are two vertices such that u1, u2, such that u1 is connected to v, u2 is not connected to v, but the neighborhood of these vertices in S is the same. What does it mean? The vertex S, the set S, is disjoint from the symmetric difference of this two vertices. The private neighbors are outside S, but we suppose that like all symmetric difference is large, so so we bound that V is not a function of S by the probability that there exists such two vertices that the symmetric difference is outside S, but we suppose that the symmetric difference is large, and with like 2 lines of calculation, you can prove that this probability is smaller than 1. And it's because with high probability S will hit like all large sets. Yes, and that's all.
Thank you, speaker. That's